Hello everyone, I welcome you all to the ASME Turbomachinery Technical Conference and Exposition 2021. Today I am going to present my paper titled A Reduced Order Modeling Approach to Probabilistic Creep Damage Predictions in Finite Element Analysis. Me, along with my co-author Dr. Kelvin Stewart, and we are the team from Department of Mechanical Engineering from the University of Texas at El Paso. My today's presentation will follow this outline. I will start my presentation with my motivation of my study, the reduced order modeling approach that we adopted for this study, my research goal. We used a creep damage model, that is sine hyperbolic creep damage model, and I'm going to talk about different sources of uncertainties that are going to affect the creep, the result and discussion of my study. Finally, I'll conclude with some future work and recommendation. The motivation of my study transcends from the US coal fleet power plant. As the power plant efficiency and the electricity generation of these power plants are on the decline, since the turn of the century, the renewable energy and natural gas-driven power plant are on the rise. To replace this existing coal-fired power plant, there is this development of advanced ultra-supercritical power plant. So as we are shifting through the gears from subcritical to supercritical to ultra supercritical, right now we are talking about advanced ultra supercritical power plant. We are pushing the limit of stress and temperature, and in turn we are also enhancing the efficiency to a great degree. So to enhance the efficiency of the existing power plant, we have to go through some steps. We have to do the uncertainty quantification of the current plants, the FEA modeling of the system so that we have a truer representation of the physical system. We have to go through the rapid qualification of the newer candidate alloys to withstand this extreme weather condition. To reduce the cost and time for the safety inspections, we have to enhance the reliability to a great degree and these lifetime extension programs. So for the newer candidate alloys to be in service, there is this extreme requirement by the ASME boiler and pressure vessel cores that the new materials must go through 10,000 plus hours of testing before being qualified for service. So this is not impossible, but it is improbable for most of the cases, if not all. When in service, the power plant materials are susceptible to creep-induced failure. So when creep is extrapolated to low stress and high temperature regime, we can see the substantial scattering. And this scattering in rupture life can persist across logarithmic decades. So to explain this phenomena, we are throwing an inflated safety factor in the mix, and we are saying that this material is going to fail between 12 years and 24 years, which is huge. So there are few questions that needs to be answered. That is, can we improve the creep prediction technology? Can we rapidly qualify the newer candidate alloys? Can we capture these uncertainties that impact creep resistance of a material? And in this study, we are going to answer some of those questions. In this work, we adopted this reduced order modeling approach to rapidly qualify the creep properties of a complex geometry. So the reduced order models are the simplification of high fidelity complex model. So herein we take a very simple 1D geometry and we apply all the creep properties along with the testing conditions to do the deterministic simulation to compare and validate the creep damage model against prior creep data. Now we assess the different sources of uncertainty that are going to affect the creep. We establish the probability distribution functions for each of the sources of uncertainties, and those PDFs are fed into the finite element settings to do the numerous probabilistic predictions. Right now, as the geometry is simple, it takes very little time to simulate numerous times, and it also takes very little computational time and memory. Now the problem is being reduced from these numerous cases to just the extremum cases, mean cases, or the best worst cases. And those cases are taken to the more complex 2D and 3D geometry. And as the element number and the node number gets increased, this 2D and 3D geometry takes a huge time for one single deterministic predictions, let alone doing the numerous probabilistic prediction. So these numerous probabilistic predictions are reduced to just simple reduced order modeling prediction, but we are still retrieving the scatter bands that are being established these probabilistic predictions. For this study, we are taking 304 stainless steel, and the replicated creep data are being gathered from the literature. The experimental scattering of these data are highlighted in this normalized minimum creep strain rate and stress rupture plot. We can see that the replicated creep tests show substantial scattering. To quantify this scattering, we can see that the minimum creep strain rate, the coefficient of variation can go as high as 34%. For the rupture time, the coefficient of variation could be as high as 16%. So this considerable scattering for the replicated creep test needs addressing. Sine hyperbolic creep damage model has been chosen for this study. This CDM-based constitutive model consists of coupled creep strain rate and damage rate equations. The stress and temperature dependency are embedded into this rate-based equation, and these equations could be further simplified for the isothermal condition by taking this Arrhenius part equivalent to 1. And all the material constants are listed in this table, where few constants are fixed and others show stress and temperature dependency. The finite element validation simulation are conducted for both the 1D and 2D model. To do so, the signage model rate-based equations are programmed into the ANSYS finite element through updating a user creep subroutine. The validation simulation are conducted up to the rupture time. For 1D model, a single 8-noded element, and for the 2D model, plain 183 8-noded element are chosen. The equivalent stress and damage at rupture for the 2D model are shown in these two figures. In this slide, the validation prediction for 1D and 2D model are shown across isostress condition. Looking at the plots, the comparison between the experiment and the prediction are quite satisfactory. And further analysis, we can see that 2D prediction are almost superimposing on the 1D prediction. And analyzing the graphs, we can say that the percentage error in ductility prediction tends to be more than the percentage error in the rupture prediction. And this variability in the prediction is attributed to the time stepping settings, the sensitivity of the minimum creep strain rate related constants, and the estimated primary creep. Now, we can assess the sources of uncertainties that are going to impact the creep resistance of a material. And these sources of uncertainties are subdivided into three broad categories. Number one, the boundary condition related uncertainties, and this includes service stress and temperature and test stress and temperature oscillations. As we know that the power plant operates well below its design stress and temperature, so that stress and temperature fluctuations are more observed in the power plant settings. While in a test setup, the ASTM standard has its own standards for the stress and temperature fluctuations. The second subdivision is the material properties related uncertainties, and that includes the variation in the chemistry and the thermomechanical processing related uncertainties. And the final subdivision includes the surface and subsurface defects or pre-existing defect related uncertainties. Because every sample, we are unaware of the fact that what kind of loading history that particular element went under in its lifetime. So it always comes with some sort of pre-existing defects. In other sources of uncertainties that include the test procedure error, the geometric parameters uncertainties, and the operator error. So all these uncertainties combine together to impact the creep resistance of a material. In this study, testing stress and temperature fluctuations are modeled by employing ASTM E8 and ASTM E139 standards. And the PDFs of the pre-existing defects and model constants are set by Anderson-Darling goodness of fit test. Now in this table, the sources of uncertainties are listed where stress and temperature are modeled by the normal Gaussian distribution. The uncertainty of initial damage is modeled by exponential distribution, and other model constants are modeled by log normal distribution. And these are the distribution plots for each of the sources of uncertainties. And these plots are shown for a particular case of 320 megapascal and 600 degrees centigrade. This slide contains the probabilistic prediction for this 1D model. So we took the 1D model, updated the user creep in the finite element settings. Then we use a probabilistic tool, ANSYS, to map the random responses for each of the sources of uncertainties into the ANSYS input deck. Then the simulation are being conducted in the ANSYS. Then the results are being processed through a MATLAB subroutine, and all these probabilistic predictions are done for the creep deformation and damage evaluation. Creep deformation, damage evaluation, and stress rupture predictions are shown in this slide. The creep deformation prediction encapsulates the experimental outliers across isostress condition. The ductility prediction seems to be agrees more at the higher stress, while the rupture prediction is observed to be vary at more at the lower stress regime, conforming to the empirical creep theory. The damage is always unity at rupture, while the damage rate remains finite at rupture. The stress rupture prediction shows the prediction encapsulating the experimental outer bounds, while the 95% upper and lower confidence bounds are shown. And the confidence bounds seems to be expanding at the lower stress regime. The quantitative analysis of these probabilistic predictions are done across three categories, that is ductility, rupture, and the area under the creep curves. The ductility percent coefficient of variation seems to be the smallest among the comparable categories, and the standard deviation and the coefficient of variation is projected to be increasing at the lowest stress regime. And the scattering of the area under the creep curve seems to be the highest, while on the other end of the spectrum, the scattering of the ductility seems to be the smallest. And the 95% confidence interval is observed to be within 2 standard deviation of mean at each cases. So at this point, we are employing the reduced order modeling approach. So we take the extremum cases from the probabilistic prediction from 1D model, and those extremum cases are retrieved for the 2D model, and the prediction is done by the reduced order modeling approach. And those numerous probabilistic predictions are reduced to only just 6 plots, but still we are retrieving the scatter bands that is being established by the 1D predictions. Deformation prediction of the 2D model based on the ROM approach is shown. So we take the extremum cases of ductility, the rupture, and the area under the creep curves from the 1D model. Those material constants and the testing conditions are retrieved from the input deck and applied for the 2D model, and the predictions are conducted. The FE 2D model predictions show the error between the rupture, ductility, and area under creep curves as low as 1.265% or less. But the most meaningful part of this part of the study is that we are reducing those 1000 1D model creep curves to just 6 2D model creep curves. So at this point, I'm going to discuss about the advantage and the limitations of the ROM approach. So the premium outcomes from a large set of experimentation are the extremum cases, the mean cases, or the best worst cases. So the ROM enables us to establish the scatter band for the complex model, and it potentially reduces significant amount of computational time, space, and memory. And the prediction accuracy for the 2D model extends the confidence to simulate a 3D model such as a turbine blade model. And it's easy to replicate the truer representation of the physical system. So on the other end of the spectrum, we have got some limitations. The ROM approach is yet to be proven across the isotherm condition, and also it needs to be applied to the larger data set of austenitic steel and candidate alloys to further validate this approach. The prediction accuracy for the 3D model will largely be depending on the replication of complex creep mechanism in the finite element settings. And we'll need a multi-stage signage that will simulate the primary creep regime as well. And finally, the spatially distributed temperature, stress, and strain field needs to be accounted for component level simulation for the overall failure of the materials. The goal of this study was to introduce the reduced order modeling approach for a complex model to reduce the computational time and memory. And to that end, this study leads to the following insights. We can see that validation simulation for the finite element 1D and 2D model show remarkable accuracy with the experiment. The probabilistic prediction for the 1D model, in most of the cases, we see the creep deformation, damage, and rupture prediction remains within the 2 standard deviation of the mean. And also the stress rupture scatter bands observed to be increasing at the lowest stress condition, complying to the empirical creep theory. And when the extremum cases are retrieved from the 1D model simulation and applied for the 2D model, the simulation shows satisfactory agreement with the prediction, and the observed percent error across the comparable categories is low at 1.265% or less. And applying Rome approach, scatter bands of the creep deformation, damage, and rupture is established for the 2D model with the minimal loss of accuracy. At this point, I'm going to recommend some future work to further improve this Rome approach. The load eccentricity will be incorporated within the finite element settings to explain the misalignment between the load cell and the specimen, the temporal uncertainty, that is the time-dependent stretch and temperature variability for the entire duration of the creep test, and the spatial uncertainty, that is the spatially distributed pre-existing damage, the stress, the temperature, and strain fields. Slide, I am going to show you the spatially distributed initial damage field. So spatial uncertainty is a parameter whose magnitude and position is uncertain, and it can be truly random and can be expressed as local distributions such as spatially uncertain defects near the surface of a specimen. And this spatial uncertainty can be of initial damage, material properties, to temperature, stress, strain fields, etc. So these demo simulations show a truly randomly distributed initial damage that is being evolved from an initial number to the unity at the rupture of the element. Finally, I am your presenter. Muhammad Abir Hussain is working as a doctoral research assistant at the team Merge here at UTEP. I would like to thank my co-author, Dr. Calvin Stewart, who is also a director of the team Merge. I would also extend my thanks to the funding agency to keep the research going. I would like to hear your valuable feedbacks on this work and your end of story after watching this presentation. I promise I will answer every one of the questions that is being asked. Thank you.